Hi, I'm Mark Weitzman. Welcome back to the review tutorial on Lorentz transformations, part 3. And when we finished last time, I had written out the boost matrix for a general Lorentz boost with parameters eta, and eta is known as the rapidity parameter. And the first thing I want to do is to write eta in terms of things you're more familiar with, velocity, etc. I'm not going to write down the whole boost matrix again, but I do want to write down one part of it. Because that will help us get these parameters. Remember that the carets on the etas are just directions. Eta is the magnitude of the boost vector. The rapidity vector has components nx, ny, nz, and I'm also writing it as eta times n eta x caret, eta y caret, eta z caret. Okay, so when we apply a boost transformation, especially from the active viewpoint, what do? We have a particle and we speed it up. I guess that's why they call it boost. So imagine we have a particle. Oh, and then there's all other stuff here. I didn't write down this stuff because I won't need it. So imagine we have a particle that's sitting at rest at the origin of our coordinate system. And we can parameterize the word line of the parameter of the particle by tau 0, 0, 0. So this corresponds to t, this corresponds to x, this corresponds to y, this corresponds to z. The parameter that we use, I'm using proper time here, but it could be any parameter. But this is a word line which just sits at the origin no matter what tau is. So when we boost it, we get a new word line for the particle. And the reason why I don't need these is because these three are all 0. So when we multiply this out, we're going to get a parameterized word line that looks like this. Tau hyperbolic cosine eta, eta x caret, tau hyperbolic sine eta, eta y caret, tau hyperbolic sine eta, eta z caret, tau hyperbolic sine eta. Now, this word line, again, this is like, I'm using the same just a different notation. We're not changing coordinate systems here or anything. This is the x0 coordinate will be that, x1 coordinate, so on. So the particle is moving along this word line. How fast is it moving? Well, we see that the equation for this word line is that xi is equal to eta caret I times hyperbolic tangent of eta, just separate it out, make it times x0. Just multiply it out. If I substitute x0 here, I get tau cosh eta, tanh eta, cosh eta, or sinh eta. So I get eta caret tau sinh eta. So this is the word line. And so you can read off over here, these are going to be the velocity components. So Vi is equal to eta I caret hyperbolic tangent of eta. And so since we know that this is a unit vector, when we take the magnitude of the velocity vector, This is 1, so we know already that V is equal to hyperbolic tangent of eta. That's the key equation. So many of you will remember that. And then from that equation, using simple hyperbolic tangent identities, we get that gamma, which is defined to be 1 over the square root of 1 minus V squared. Remember, C is 1 in everything we do in this course. And this is equal to hyperbolic cosine of eta. And then gamma V is equal to V over the square root of 1 minus V squared is equal to hyperbolic sine of eta. And the vector V itself is just equal to eta I caret times tangent eta. So now we have everything. We have the relationship between our eta parameters and our velocity parameters. So now I'm going to write down, this time I'm going to write down the boost matrix for eta. I'm going to call it now the boost matrix in terms of the velocity vector. We're going to substitute, and this is equal to, and this is really the main result of this whole tutorial. It's going to be gamma Vx, gamma Vy, gamma Vz, V is components, Vx, Vy, Vz. It looks pretty on the time component parts, but again, it's the same sort of ugly thing on the rest of it. 1 plus gamma minus 1 Vx squared over V squared. All the diagonal ones are basically the same. 1 plus gamma minus 1 Vy squared over V squared. 1 plus gamma minus 1 Vz squared over V squared. And then on the other ones, we lose, it's just cross products, so we lose the 1. Gamma minus 1 Vx Vy over V squared. Gamma minus 1 Vx Vz over V squared. Gamma minus 1 Vx Vy over V squared. Gamma minus 1 Vx Vz over V squared. Gamma minus 1 Vy Vz over V squared. Gamma minus 1 Vy Vz over V squared. So this is it. And this is a general, if somebody ever tells you you have XYZ coordinates and you're boosting with these velocity components, this is the boost matrix. Now, just to check my work, you can compare with the standard book by Jackson on classical electrodynamics, the second edition I have, which is probably the best edition before he went to MKS units under pressure. And look at section 11.7, page 541. They'll have the same matrix. The only difference is they'll have minus signs on these parts over here because he's using passive transformations. I'm using active ones. Okay, so let's get back to that final theorem that I wanted to show, that lambda is equal to RB is equal to B bar R bar, or P prime R prime, uniquely. I'm not gonna show the uniqueness, it's not hard, and I'm only gonna show one direction here. I think I'll show this direction here. So given a Lorentz transformation lambda mu nu, first thing you do is you define the velocity part of it, and it turns out to be very easy. The velocity part is given by lambda r0 over lambda 0, 0. Now, if you go back to our first lecture on item number 3, which I'll write down again, that lambda 0, 0 squared minus lambda I 0, remember to sum over I is equal to 1. So if instead you write it as greater than or equal to 0, you'll get that v squared is less than 1, which is what we want for velocity. So this is a legitimate velocity, and now what we do is I'm going to start showing how this works. First of all, let's calculate b minus v, the 0, 0 component. Well, we know it doesn't matter whether it's minus v or v. We know the 0, 0 component is gamma anyway. And gamma is defined as 1 over the square root of 1 minus v squared. Square root 1 minus v squared, which is equal to 1 over the square root 1 minus lambda r0, lambda, keep writing a instead of lambda 0, 0 square. And this is equal to lambda 0, 0 divided by the square root of lambda 0, 0 squared minus lambda r0. And using this equation again, only now we'll use the actual equation where it's 1, this is equal to lambda 0, 0. Okay, that's good. Now let's calculate b minus v 0r. So if you look at this matrix, the 0r or the r0 component is just gamma vr. So when I use minus v, it's going to be minus there. It's equal to minus gamma vr. Remember, we defined vr by that. So this is minus gamma lambda r0 over lambda 0, 0. Gamma is, which is equal to minus lambda 0, 0, lambda r0 over lambda 0, 0. It's minus lambda r0. Okay. Now I'm going to define a new Lorentz transformation. I'm going to call it R. And it's just going to define this as the boost b of minus v times lambda. Now, the Lorentz transformations is a group, and so the product of two Lorentz transformations is itself a Lorentz transformation. Now, let's calculate what R, let's calculate the 0, 0 component of R. This is equal to b minus v 0 mu, just matrix multiplication here, lambda mu 0. Okay, and put a comma here. And so now we just, mu goes from 0 to 3, so I'm going to get b minus v 0, 0, lambda 0, 0, plus b minus v 0 I, and this, we're going to sum over I, lambda I 0. Okay. Now we already established b minus v 0, 0 is lambda 0, 0, so we got lambda 0, 0 squared. B minus v 0 r or 0 I is minus lambda r 0 or I 0. So this is going to be minus lambda I 0, lambda I 0. And this, we're back to this identity again, which is equal to 1. Okay, so this is very good news, because we know that if we have a Lorentz transformation and the 0, 0 component is 1, it's a rotation. So R is a rotation, and now we're just going to rewrite lambda. Lambda equals BV times B minus V. We know this is the identity. I mean, we can establish it and you can prove it, or you can multiply out these matrices, but you should know that BV and the inverse is just the opposite direction. That should be obvious. And then times lambda, okay? And this is equal to BV is equal to BV, which is that. And then we define B of minus V times lambda as R. And this is our proof. Because we know this is a rotation because its 0, 0 element is 1. And we know this is a boost. By definition, we defined them. B matrices as boost matrices. So we've done the factorization as the B times R. R times B is similar. Showing uniqueness is almost trivial as well. So this ends our tutorial. There's a lot more we can do with the Lorentz and Poincare groups, and when we come to spinors, we'll start talking about all the representations and how to combine representations. But that's more quantum. What we did here, it has nothing to do with quantum mechanics or quantum field theory. It's just classical physics and how to decompose Lorentz transformations. Thank you very much.